Greetings, and it is my pleasure to welcome you all again to this course. We have seen so far illustration on the performance by different approximation method used for convection term, time advancement or integration methods available, arrangement of variables, need for pressure velocity coupling, 4 methods we said we will take to explain. We have already seen Mach simple algorithm, and today's class we are particularly going to see variants of simple, that is simple R and simple C, and projection method. For the sake of completeness, we will go back and see what is pressure velocity coupling. We know there are 3 momentum equations for 3 velocity components and 1 continuity equation. Velocity term appear in all the 3 equations as well as continuity equation. Pressure term appears in all the 3 equations for momentum. There is no separate equation for pressure, though pressure gradient term appears in all the 3 momentum equation. Otherwise, you have 4 variables and 4 equations, number of equations equal to number of variables is satisfied. Velocity variables in turn, they are coupled because each velocity term appears in every other equation, hence there is a strong coupling among velocity components. And correct pressure should be specified in the momentum equation to get correct velocity field which satisfies the continuity equation also. The procedure to link between momentum equation and continuity equation, a procedure called pressure velocity coupling is used. The linkage is set through a procedure called pressure velocity coupling. We will have a relook at simple procedure using the initial guesses for velocity u star v star and pressure p star. Momentum equations are solved. Pressure correction equation is set up based on this guessed field in the continuity equation. When you solve the continuity equation, we get pressure correction term, and this pressure correction value is used to correct pressure as well as velocities. Using the above pressure and velocities, one can solve any other transport equation as well. The process is repeated until the convergence criteria is satisfied. A simple algorithm is shown in the flow chart as here. We start with the guess values, solve the discretized momentum equation to get u star v star, and this is used in the continuity equation to obtain the pressure correction equation. Once you solve this equation, you get p prime, and that is used to correct pressure as well as velocity as shown here. Once you solve pressure, velocities, then you can take up any other scalar equation which is given here with the symbol phi. You can follow any finite volume procedure to get discretized equation for transport equation also. So, you solve this and you get phi, and you check all of them for convergence. If convergence is satisfied, you can stop the iteration there. If it is not satisfied, you need to repeat this procedure. Before repeating the procedure, whatever value is obtained in this step as well as in this step, that is pressure, velocity as well as any scalar variable, are reset as guess pressure, guess velocity and guess value for the scalar to proceed to the next iteration, and the process is repeated. So, this is algorithm for simple. There are 2 versions available, variants of simple. First one is what is known as a simple revised. In short form, it is also called simpler. In this, the discretized continuity equation is used to derive a discretized equation of pressure instead of pressure correction equation itself as in simple. The intermediate pressure field is obtained directly without the use of a correction equation. That is the difference between simple algorithm and simple R, and velocities are obtained through velocity correction itself as in simple algorithm. Another variant is simple consistent, in other words simplex in short form. This was proposed by Van Toormel and Rejbij in 1984. It follows almost the same step as simple. Few additional steps are introduced initially to get guessed velocity as well as pressure. We will look at those steps in the next slide with the algorithm flowchart displayed. The simplex velocity correction equations omit terms that are less significant than those omitted in simple algorithm. If you recall, important step in simple algorithm is you drop the term correction contribution from the neighboring nodes, that is sigma a n b u prime n b, that is a neighboring node contribution, and that term is dropped, and that is an important step in simple. Now in simple C also you will drop important term which are less significant than those omitted in simple algorithm. Without going to the details, we have a flow chart to explain the simple C algorithm in detail. So here we start with the initial guess, that is the initialized condition P star, U star, V star and phi star. So we calculate what is known as a pseudo velocity as shown here, and if you look at that expression, this is a discretized momentum equation, sum of neighboring nodes plus source term and coefficient for the corresponding interest node as shown here. Similarly for the second velocity component V, again corresponding velocity coefficients and neighboring nodes contribution plus source term that is there in the V momentum equation. So this is basically a discretized Navier-Stokes equation, only thing it is applied for different situation. So if you solve this equation, you get U cap and V cap, that is used in the discretized continuity equation to get pressure, equation for pressure as shown here. So once you solve this equation, you get P. Now this P is set as P star, and this is a starting step for simple algorithm. So when you compare simple and simple C, you have two additional steps, and these two additional steps are introduced to get pressure, and this guess pressure is supposed to be closer to the actual pressure because you obtain from solving the continuity equation, which is again obtained using U cap and V cap obtained from the momentum equation. Now after this, the steps are same as in simple. So you solve discretized momentum equation, you get U star V star, then you set pressure equation, then you set pressure correction equation. So P prime is obtained through the pressure correction equation solution, and then velocities are corrected. So you have two additional steps introduced when compared to simple in simple C. This is followed and you get P, U, V and any other scalar. Any other scalar phi, again you solve transport equation, discretized form of the transport equation for the variable phi, and you check for the convergence and you stop if convergence is satisfied. Otherwise repeat this procedure to go back to the first step, that is again starting from guess value and proceed. So simple C, you can immediately make a guess. It takes slightly longer time in the initial, but then comparatively it takes less time because the guess pressure as well as guess velocities are closer to the actual pressure and velocity. So we have seen in detail two important algorithm, simple and simple C. Let us go to the next method, what is known as a projection method. The projection method for the solution of incompressible viscous flow field, and it is based on theory what is known as a Helmholtz Hodge decomposition of velocity field. So, this decomposition theory states that any vector, any velocity vector field u on a simply connected domain can be uniquely decomposed into a divergence free, which is called solenoidal part, and an irrotational part. So, in the projection method, the first step as in the past is to obtain intermediate velocity, and you denote it as u star, and it is computed explicitly using the momentum equation, with one big difference here is you ignore pressure gradient term. So, pressure gradient term appears in all the three momentum equation. You drop the term, then you have only convection term on one side, you have a diffusion term on the other side, or any other source term. So, if you drop the pressure term, whatever velocity field obtained is the intermediate velocity field, and you denote it as u star. Then how do you bring the pressure into the system? You set up what is known as a pressure Poisson equation. The pressure Poisson equation is solved, you get pressure, then the velocities are corrected. So, pressure Poisson equation we have already seen, it is a elliptic equation. Now, in the next slide I am going to explain how pressure Poisson equation is obtained for 2D. So, in the last step, velocities are projected onto the divergence free space using the computed values of pressure. That is, you solve the pressure Poisson equation, get a pressure, and that is used to correct intermediate velocity field u star and v star, and that is supposed to satisfy divergence free condition, that is continuity equation. We write down here the incompressible Navier-Stokes equation in differential form as shown here. So, dou E by dou t plus u dot del u on the left hand side equal to minus 1 by rho del p plus nu del squared u. So, you obtain intermediate velocity field u star by neglecting the pressure gradient. So, you get u star minus u n by delta t corresponding to the time derivative term equal to the convection term is now taken to the other side. So, you have u n dot del u n plus the viscous diffusion term. Now, in this superscript n stands for the previous time level and star stands for the current time level. In this case, star refers to intermediate velocity field to be obtained from by solving this equation before proceeding to the next level. So, if you solve this equation, you get u star. Similar to u star, you will also obtain v star. So, u star and v star are used to obtain what is known as the pressure Poisson equation as shown here. So, del squared p nu time level n plus 1 is related to intermediate velocity field as shown here. So, this is the linkage between velocity and pressure. So, once you solve this, you can correct the velocities. So, intermediate velocity is projected onto the divergence free space, and that is corrected as shown here. U n plus 1, which is the new or corrected velocity, is related to the old or intermediate velocity, and with the correct pressure related as shown here. So, in this pressure Poisson equation, you have a source term on the right side. The source term is obtained by using a intermediate velocity field. If the source term goes to 0, then you have the equation what is known as a Laplace equation. With the source term appearing, this equation is called pressure Poisson equation. Now, in the next slide, I am going to show how a pressure Poisson equation is derived for two dimensional situation. Let us rewrite the momentum equation. X momentum equation is as shown here, and y momentum equation is as shown here. So, what do we do? Differentiate x momentum equation with respect to x and y momentum equation with respect to y, and you add both of them together. So, that will result in pressure Poisson term on the left side and corresponding source term on the right side. In general, that is for 3D, then all that you have to do is take divergence of the Navier-Stokes equation and use divergence free condition wherever possible, simplify to get pressure Poisson equation. So, in this week we have seen in detail time integration methods, various methods available, Euler method, multi-point method, and then how to obtain predictor corrector to get higher order of accuracy. Arrangement of variables, collocated, staggered, semi-staggered, advantages associated with each one of them, need for doing a pressure velocity coupling, and detailed explanation for 3 methods, that is Mach algorithm, simple algorithm, and projection methods. Some part of the lectures on simple algorithm are adopted from a book, The Finite Volume Method, authored by Versteeg and Malalashekara. Thank you, and we will see you in next class next week with some other interesting topic. Until then, have fun. Thank you.